All right, cool. So I think Xian shared the paper as well. Application. So you guys can see it as well. Present to everyone. Okay. So essentially, do you guys have any questions for the Q learning part? You actually went through the videos and the papers, and do you have any questions for Q learning section? Underlying problem of Q learning is in this MDP. What do you mean by underlying problem? No, no, no. We went all the way up to Q learning. That's it. Yeah. Mhm.
I would say at least somewhat. And the formulation children use action space or stay space.
Yeah, I think it's just a convention to model these things as Markov decision processes.
Are you asking, is there any other way to do key learning other than using MDPs? Or we actually were discussing this last workshop. Maybe there is some. I think the common framework for any reinforcement learning is just to represent the model and the environment, right? So, and it seems like MDPs are the best way. Maybe not the best, but at least the most popular ones. And every yeah, yes, we're assuming that right.
Limited knowledge, yes. Because from the papers I've seen, I haven't seen one otherwise. So,
Yeah, I think by default all the RL agents they assume that there is MDP underlying. And it's funny, like when you look at the code of an algorithm, right, of reinforcement algorithm, it's just a table, right? For example, for Q learning, or like for policy iteration in some, I'm not sure if it's stable as well. But when you go behind the code into like the math and theory of that algorithm, it usually built on MDPs. That's like what we observed so far. Okay. And the whole idea with the key learning, we already know the state action pair, SARSA or whatnot. Okay, so let's then try to figure out, let's build some intuition on how does the deep learning comes into play. Like what would the deep part of the reinforcement learning? Because I got, okay, let me, maybe I'll start first. I'm gonna tell you how I understood it and maybe we can just elaborate and make sure we understand, we're all on the same page. So our agent trains on some sort of state, right? So for any type of learning, we need a state, action, reward, end state, SARSA essentially. And for example, for Q learning, we need those four at least, and transition probabilities. So how do you represent a state? If it's a grid world, then we kind of know how the grid world, how to represent the state of a grid world. But in the case of video games, for example, how do we take image from sensors or video? How we take that image and represent that as a state? If we count into the combination of every single pixel, it would take like forever. It would be, the complexity of the space is going to be just too great. That's why what you want to do is you want to pass it through a neural network that extracts features that are important for you to make a decisions on. Maybe the presence of an agent, maybe where the enemy is, and so on. But the whole idea of neural networks is that it extracts those features, right? It does it for you. and then you take those features out and you feed them into your reinforcement learning agent. So instead of that being pixels, it's some sort of vectors. So instead of 84 by 84 by 4, which is the 84 pixels by 84 pixels by 4 channels, you end up with, like, let's say 512. It's so much easier to train on 512 um, vector space rather than the other one with more complexity. So, and then having those as an input for your state, then your learning agent trains, which is, okay, if I see this, I do this. If I do this, I move forward. If I do this, I sit down, I shoot, and so on. So that's the part. It just takes it as R. I mean, as a state. Now, the part where I'm a bit confused with RL, how do you how do you make that neural network learn for any video game, for any image? Because essentially, first you have to teach that that neural network to extract useful features. In this case, to me, it seems like you have two learning agents learning at the same time. One is trying to learn, okay, what features do I need from that image? And the other agent is like, okay, based on these features, how do I learn which actions are the most relevant?
I said something. So I think the deep learning part
Mm-hmm.
is not to use it to extract the pixels and turn it into features. It's not for feature extraction purposes.
Oh, what is that for?
It is for approximating the word for the pixel. So you input the pixel into the deep
Yeah.
neural nets, and then it approximates the word.
Yeah.
And then it learns that by putting following the algorithm. Like, so you move this, and then it will approximate something, and then it will learn the hard truth. So if we approximate right or wrong, then you have your error, then you run this again. And it's like online learning. You run one example, one example.
It could actually be both though. Like that was
Yeah.
the deep Q learning when they
So
solved all the
that is the human.
yeah.
Mhm.
Yeah.
What you were actually describing sounded more almost like the world model thing,
Mhm.
where they had one model that was compressing the state space down to some low dimensional vector.
Mhm.
Okay.
Then there's another model that's like deciding what's useful out of that compressed
Yeah.
state space. And then there's actually a third model that was learning what actions to make.
So I think what he's talking about is the model-based algorithm, right?
Yeah.
So, but then, so this one I'm talking about is like the model-free one.
Yeah, the deep Q
And
one.
then just do the DQ, and then just, yeah, use it for possibly the, the reward.
There is that big distinction on model versus model free.
Yeah. The model the output of the reward. You try to guess you try to predict the reward. Like it's a supervisor. Okay, so given the pixels, given the state, yeah. Yeah. And then based on what Ivan said, so the pixel huge. So that's also true. And then that is the problem with the Q is that if you have just a very simple game like, I don't know, 5x5, it's very easy to have just a table, like a dictionary table, to store all the moves and stuff,
Mhm.
and you just do a hard lookup, right? And then the problem is when you're there's no way you can store that, so that's why you use the deep to approximate.
Yeah, it also allows you to think of like split situations too, right? To decode it,
Yeah.
and you can recognize things that are close in state space,
Yeah.
such that you can use kind of the same strategy when you have the same kind of situation, even if you're in like totally different action places. If like the local world is the same or something like that.
Okay, so just to make sure we're on the same page, right?
Yeah.
For deep Q learning, is what you're saying is the deep neural network part of it
Yeah.
is used to approximate rewards.
Yeah. Predict the reward.
How does that work? So let's say you're playing a game, right?
Yeah.
Atari. So that game, like deep learning.
How do you choose the action? So it will provide all the actions. All the reward will act for all actions, even the states.
Oh, okay.
If you do a problem,
So yeah, approximately discounted.
and you pick the best.
You like
Atari?
deep Q learning to solve Atari
Yeah,
games.
yeah. So your input is your state, and then you calculate the reward for every action, every possible action,
I posted
and
actually.
then
You also post something.
yeah, you can
I posted the TS video. They should have the link to paper.
Okay, let me just ask this question real quick. So in this case, right, this is the game, Atari game, right?
Yeah.
So the input is 84 by 84 by 4 channel, right?
Yeah.
This is the input image, and then this is the actions that you have available is left and right, right? Okay, so the reward, you're not getting reward until the ball hits the square, right?
Yeah.
So how can you approximate the reward based on the neural network, with the neural network?
Part of it is that like the reward comes way at the end. So
Mhm.
like you have this like discounting factor. So there's a bunch of rewards. For you run this one policy, it'll run for a long time, collect a bunch of rewards, and then you can discount back the rewards and then do the updates of the weights of the network. Once you kind of finish the run.
Yeah, there's until the end. You there's like an episode. So you run the whole thing until and then so I don't know how Atari coded the reward. So that's also an issue, like with the late reward or because there's like at the very end then you die and then the intermediate steps have no reward, right?
Yeah.
So yeah, that's a problem and then there's some way to solve it.
That's actually one of the problems they had is they found it in that paper. It got really good at solving the games that had regular rewards.
Yeah.
But games where the rewards are very sparse, we
Yeah.
actually had to plan
Yeah,
something
it's
out
a-
just to get a
it's a
start. It couldn't solve it.
Also, I couldn't do Mazoot's whatever revenge. Yeah.
Which one? What is that?
I'm gonna post a picture.
It's some hard game where there's like a bunch of traps everywhere,
Mhm.
and you only get rewarded like, once you get super far.
I see. Okay.
Yeah, the sparse reward is a problem. So there are some ways. Actually, I forgot what it is. Do you remember what are the ways to solve this kind of? I think you have to just assign like a small reward.
It's I think it typically involves hand coding. By hand coding, I mean you come up with something new.
So what I
That's
saw,
one way.
the theory of work, what I saw was whether or not you saw something new.
Curiosity.
Yeah, curiosity. It seems like that's the main one that specifically Vermont is using in a very unique way, but it's basically the same problem.
Yeah, so it's essentially you figure out a way to guide it. If there's a novelty, then this is intrinsic, the extrinsic, intrinsically, it feels okay, yeah, it's what it should be. The funny thing about curiosity is that they simulate a TV stage, like TV on the wall in the environment.
Oh, yes.
And then the agent just got stuck there because it keeps changing. So that's the fun part of curiosity. Exactly the human problem.
Experience replay was another really important part of this paper.
Yeah.
Like fixing since the policy keeps on changing, like the actions it's choosing, like its reward space kind of changes as well, and so you have to decouple that somehow. And so what they did is just take select experiences from the past and randomly sample those, and then train it on those instead of just what's happening at the current time. So it's not on policy, it's off policy method.
Okay.
Sorry, are we talking about this paper?
No. These are the papers recommended.
Just the idea of the
Okay,
team.
that one.
So yeah, let's try to figure out exactly how the network is used, the CNN, convolutional neural network, or whatever they use, like where the deep part is coming from. Because I think right now we have like two theories. One is to simplify the state space, and the other one is to approximate the rewards.
So what's the difference between those? Because you guys mentioned a few seconds ago that there's a model free and a model version. I'm still not clear what it is.
Okay.
Yo, take a look at what I just posted in the chat.
Who was talking about the model free and model?
Well, you mentioned something.
All right. Let me see.
Model based would be like a game like chess, where like you can just simulate ahead. If you have a perfect model of what's going to happen.
typical model is, I don't know, actually I don't know the model base, I haven't read it, I only know the model tree, but the idea is that you can approximate the world, like the total environment. In the model tree, there's before that, you don't do that approximate.
Oh, I see. So all the Atari games would fit under model tree.
I
Yeah,
have,
I think, yeah.
I have the Udacity lecture on intro to deep learning.
Mm-hmm. Intro to deep learning.
It seems like we're asking like what is,
Yeah.
Well, I think the model versus model free depends on the algorithm. It's the implementation thing. Right?
yeah, so I think this is primary model.
Like I think like the world of current models, that was like a model base. Because you're learning some sort of model of the world based on decision.
Could you share your thing on the Slack as well?
Like do you want to look at it?
Udacity, sure.
I also have another blog I'll post as well on model free for this particular game, Montezuma's Revenge. This is on openai.com.
Okay. We should ask Alok. Like Alok is. Alok is. Are you there?
Alok?
Oh, this video. Oh, it's cool.
I found a good one-liner about the model versus model free.
Alok,
Can you hear me?
Yeah.
Yeah, so for the model-based learning, usually have some idea of the transition probabilities. That's the difference between that one and model-free learning.
Basically, the question is, can the agent make predictions about what the next state in the reward will be after it takes each action? If it can, it's model-based. If it cannot, model-free.
Yeah.
It was correct. Not a huge space. Whether or not there's a null or not, there's a huge space. When you're trying to reduce it to the valuation or the
Reward.
the reward function. It's just that the reward function now, instead of being like this concrete, discrete, kind of like grid world type thing, it's more of like a landscape of with continuous space. It's like this slightly different input, this slightly different input, and you're trying to like create a like, I feel like it's still what you're saying is still relevant.
Yeah, so there's two.
So
application of two things.
yeah, so I understand how do you reduce this state space complexity using neural networks. So that's the whole idea. You extract features and then you train based on them. So that makes sense. And that's actually the reason why in many CNNs that are used for deep reinforcement learning, convolutional neural networks, you don't use pooling. Because pooling eliminates the position. Let's say there's a pixel, and let's say there is a cat at the top or left side, right? If you do pooling, that you lose that information. Yeah, convolutional neural networks. If you do pooling, then you no longer know that cat was on the top left. So that's why in the when at least for these Atari games that they had, they don't use pooling. Okay, so that was my understanding. Okay, so you have this very complex state space. Then you reduce it, just extract features, and then based on those features, you train your reinforcement learning agent. So it says like, oh, okay, I see a dude, right? This guy is like on the bottom right, and it looks like an enemy. I'm gonna shoot that guy.
Which paper are you talking about?
So that insight I got from the video that I posted. I keep getting more and more papers. But now when it comes to the reward part, right? I think my understanding, the whole reward and how you delay it and how you discount all this reward should be handled by the Q-learning agent itself. So the way I see it is the Q-learning is the brains and the neural network is like an eye, like a sensor that processes the information. So as soon as I'm not sure how do you encode the rewards into the network itself. So Alok, it seems like maybe you know this thing. Can you help us?
Sure. Actually, I just posted a link to one of the textbooks that would be pretty useful. I don't know if I can explain very well not being in person, but in terms of visualizations, it's done pretty well in the textbook that is provided here. Xiang, if you're there, you can probably guide them through.
Oh, I haven't read the book.
Oh, you didn't get to that part? All right.
Where does it talk about sparse reward? I was
What does it talk about? What? Sorry.
the sparse reward problem.
I don't think I only got chapter 1. If anyone can
It's
send me 2 to
probably
4.
a bit, I forgot where you talked about it. I couldn't-
Oh, does it only have chapter 1?
You have to
Oh,
like get
four
tokens.
chapters.
How do you? We need tokens for the rest of the chapters, right?
I
That's when you guys had the PDF that was all 4.
Oh, okay. Yeah, I see.
Yeah,
you can find this on the RL thread. There's a thread here.
Yeah, but the
On
one
Slack.
only had 1 chapter.
But I uploaded another one.
Sorry, the other one does have 4 chapters.
Okay, I gotta find that. If you can repost it, that'd be great.
Yeah, sure. I'll It's actually on the Slack, but I can repost it again. Sure.
Oh, can you post it on the Slack?
Yeah. Just a second.
Are you wanna switch to the? We have a HDMI cable. No, it's not HDMI.
So I guess I'm really confused what you really are feeding into the neural network, because I'm getting the idea of the state, but the thing is, it seems like the environment dynamically changes as the agent interacts with it. So is it like a reiterative process where it's looping back into itself and it's like online? Like, how's this working?
What do you mean the environment dynamically changes? So
Well, the features that you're extracting, right? I would imagine at each state, at each time that you're like viewing the system or whatever, and the agent is deciding his decision to make, that is going to change what features you see in the environment based on how it's played. So in this Atari game, you might have the first and second layer removed if it's a little bit later that you're in the game. You know what I mean?
You mean to say the first and second layer of the neural network itself?
No, I mean literally in the Atari game, like the first and second layer of bricks literally might be gone, or some that might be missing. So the environment that you're interacting with is no longer the same as like this initial state that you might feed into the neural network. You have to keep feeding it states, right?
That's right. So in that case, if you can compare that to, for example, having a image, in that image, it would be equivalent to having particular channels which are turned off, right?
Sure. Yeah, that makes sense.
Does that make sense? So if you can compare it that way, you'd only need to look at it as having an image which is changing over time.
So I guess this works really good for things that are like kind of finite state where you can turn off those channels or whatever you want to call them, because in an Atari game, we kind of know there's only so many states and finite combinations that you can make of plays. But what about in more general environments, I'm wondering?
When you say more general environments, you're thinking back to deep traffic, right?
I'm actually thinking like in finance, or like just a more complex environment than a simple thing where you can have 2 actions and the states are literally something that you and me on a piece of paper for like an Atari game with, let's say, 30 or 40 pieces layered at the top. We could sit there for a few hours and we could just on pen and paper work out every possible state, I think. I don't think it would take that long to see all the different combinations. Whereas in a lot of other things, I think there's much bigger interactions that can occur between the environment and the agent. Like there's many more combinations. So I'm wondering how you deal with that type of stuff, because Atari is a really kind of simple problem, I guess.
Yeah, I have some idea, but I don't know. I would not want to speak to that because I'm not quite sure. And it's like, that's definitely one of the reasons why there are difficulties scaling up reinforcement learning.
All right, no worries, man. I don't want you to talk out your ass, but I'm kind of curious. I think a lot of us in the group, so maybe we can figure this out as we go along, because I do know that reinforcement learning is being used for more serious stuff now. That's much more complex.
Okay, so where were we? Did we figure out the network part? How network is used? Do you guys understand that?
Yeah, I attended the TDLS session on that paper, and I got really familiar with it from there.
Or could you guys explain whether it's reducing state space, whether it's doing the reward part, or what it does?
That one's an approximation, but it's a lot of clever tricks that they're doing as well. Like they're not even looking at like 1 frame, look at 4. They only update their estimator every so many iterations using the experience replay. There's a lot of moving parts.
All right, so let's go.
Like the learning between the neural network can be a Q function.
Yes.
I think I basically understood this. What I thought of in my mind of an analogy was, imagine you go from like one school in one country and another country to another country.
Mhm.
And you have a whole bunch of rules in your mind as to how things are supposed to work based on like teacher says this, teacher says that. And you go to the next one and the rules are slightly different. So you start applying the rules based on what you know from one to the other, but the rewards are slightly different than what you expected.
Yeah.
You start trying to close the gap between those.
Yeah.
So that's the way I understood it. So that's the connection between the reinforcement part and the inputs that like you know what I mean by inputs? Like basically if this teacher says this, I'm supposed to do that.
Yeah.
But then it's wrong in the other school because it's in a different country, so they have different rules. And
Yeah.
so you have to figure out what's the difference between those two and try and adjust your understanding of what connects to what based on this loss.
Well, this is the Bellman equation essentially. This is what you did. You just described the how policy is being updated.
Yes and no. Yeah, well, there's the Q part, which is like how it. Like, can you explain what you mean?
Okay, so what you just said is essentially, I have my own policy, but now I'm in a new environment. How do we adjust to this new environment? You just change your policy, and the way you change your policy is by updating your Q table that you have, for example. And the way you update it is a Bellman equation, which is the Q learning.
Yes, but then the loss of the, so there's an updating of the Q table from what I got, which is the difference between what you thought the reward at a particular state was going to be
Yeah.
based on this neural network and what it actually turned out to be.
Yeah.
That becomes the loss, which you then plug right back into the neural network.
Talking about this essentially, right?
Exactly that.
Can
You got
you?
the Bellman equation and you've got the loss function that includes the Bellman equation.
So what you're saying is you measure the loss using neural network.
You measure loss based on the difference between what you predicted. Like again, with the school, I thought doing this is going to be great, and then it wasn't. So now I have to go back and say there was this difference.
Yeah.
How do I update my neural weights to make sure that I don't make that same mistake? Yeah.
And this has we're replacing the table with the neural network, which is like
Today we will talk about deep reinforcement learning.
T function and the T function at this state and the Bellman
Yes.
equation captures the T
Yeah.
function.
Yes. So that's that loss equation. Those two parts, the R plus gamma thing, and then the last part are actually supposed to be the same. Like they should be equal for your loss to be zero, right? And they are. If you take QSA, the second part, like the very end, the right-hand part, and you open it up, it should equal that. It's the current R plus gamma. So they should be identical. Difference is that you've got two different thetas, which doesn't show up here. And one of the thetas is your old beliefs that you brought from your old school, and then the new theta is what actually happened, which is constantly being updated, like as you're in school.
You get that from the environment. Like the error, the new rewards, that's what you get from the environment. Like you don't need a network for that.
No, the idea was because the state space is so gigantic,
Yeah.
you no longer have a lookup table. It
Yes.
wouldn't fit in memory.
Yeah, your lookup table is what we think of a lookup table. Sorry. When you think of a lookup table, it's
Yeah.
just a function which goes input this state, output the right action. That's a lookup table, right?
Yeah.
Well, imagine if that function was an entire neural network now. Input this
Oh.
huge state, output this, and it's not discrete anymore in the sense that it's not like this action, this action. It's more like a continuous space of possible actions with different, like, so it's like, it's a little bit more fuzzy, but still it's just an input output function.
So can we take a look at it, deep learning algorithm? I think it's on paper. Do you have a paper?
I posted it.
So
Which
that-
one? This?
Not that one. It's called human level.
Yeah, that
control
one.
of
This
the
one?
reinforcement.
I have it on nature.
Yeah. Can you scroll? No, this is not one.
I
This is
posted
the-
it, like-
this is
You
the-
posted
the original paper. I think
All right.
the-
Where do I go?
Look at the algorithm,
Right there.
then right from
The one I posted.
from there.
This?
This one is really good.
This one?
That one, yeah. Can you scroll to what pages? Keep going to section. Which section is this? Section
Tell me a page.
methods. Do you see methods? No, let's go. I can scroll up. Page 6. 7.
Okay. This?
Not this. Page 7. On the right. right column, right hand side.
Page 7, you said, right?
Yes. Scroll down. Yeah, that one, obvious one. I think this basically encapsulates. This is a bigger picture. They talk about TOS, but I don't remember exactly.
I posted a video too. I can repost that.
But essentially, I think what the Q part is basically neural network. And you have, like, periodically, when you see at the bottom, every 6 step, this step Q prime to Q. So it's kind of like sort of batch learning in a way, and you have the old one and you have the new one. The way you learn is you basically measure the difference between the old one and how it performs in the new one or something like that. Yeah, I need to look at this again. So I think essentially this captures the entirety of
the 2 Qs. That part confused me too, and I think that's the most difficult part of it, especially with the thetas. It seems to me that, like, if you update the Q with every single reward, it becomes too overreactive. It's kind of like it's reacting to every single thing, almost like it's getting too, like, emotional. Every single thing's causing it to go a certain direction. So you don't update your, like, beliefs, which is the old Q, except in certain batches. It's kind of like you take the lessons of the day and then, like, update it at the end of the day. This is the part that gets kind of difficult to explain. You still keep acting according to your old beliefs and measuring the loss between what you did and what actually happened until the end of the day, at which point you batch change the entire, your set of beliefs, like at the end of the day. But you don't update your actions and beliefs during the day.
It's like back propagation of batch.
Yeah, it's exactly this type of parameter.
Yeah.
Since you got to decide how reactive you want.
Well,
Okay, but
and also there's periodically, that's what one is that is online already, because periodically you perform gradient set and you swap the new video.
Yes, you swap it out.
So that's why it's online. So you don't have to wait for a bunch of episodes for them to do this. You can do it online. Yeah. Actually, when they're doing it, for the entire games, they're actually doing this online, swapping out very rapidly. So they adapt as they go.
So
What's the distinction between online versus
Offline, like for example, policy gradient is offline. So in that case, you with a fixed policy, you play with a whole bunch of times, you get some samples, and then you update. That's offline.
So you only update your weights after that.
Yeah. But this one is you are capable of updating very rapidly. You swap as you learn. Yeah. If you want to see something.
It's kind of off policy though, because the whole experience replay thing, right? Like it's learning from past experiences.
Policy.
Like, yeah.
There's no policy model for
Okay, but from what I understand, like, yes, it's learning as it's going, but it's learning from like past stuff that's happened.
Yes.
So it's not like the immediate thing, right?
I think that was like an enhancement.
Okay.
Like it's somewhere in here, but that was actually it's somewhere there too.
Sample render mini battery transitions.
Alok, do you have something to add?
Yeah, that's that part there.
You mean for the off policy part?
can you see our screen?
Can you see the screen?
Yeah.
All right. So
Yes, the off policy part.
So on policy is when you're using the policy that you directly calculate using the Q values. But off policy means you're not actually using that one.
off policy learning is when you did something burned and then you're like, okay, this is what I should have done. Or when you already have a model and you just solve the MDP world and then like, okay, this is my new policy.
When you have a model, you solve it? What do you mean?
Okay, so you know, if you have a MDP, right, with all the transition probabilities, with all the action and states.
That's right.
Right? Then you can just calculate the whole policy. Like, you don't have to go through it. You can just calculate it, right? And that's what the policy iteration and value iteration do, right?
Yes, that's right. Okay, that's what you mean. Okay.
Yeah, whereas the Q-learning is you actually act on the world and make mistakes along the way, but as you live in that world, you update your policy as well.
Yeah, because you have to sample and then act on that. Yeah.
Okay, so that one is the what do you call it? Online learning.
That's learning online.
Yeah. So did I confuse you even more, or did that answer that? Even more. Okay, sorry.
I think
I think I'm confused by what you're saying.
so. The alternative would be, let's say that
Because no, go ahead.
let's say that when you calculate loss, which is the loss you want to calculate based on the difference between your belief and what actually happened. Normally, you just act, you have an expectation, and then there's a reward difference. The problem with neural networks is that if I change my beliefs at time t, then the actual beliefs at time t+1 change as well, because neural networks are kind of like big nets, where if I pull up one point in the net, the rest kind of goes up with it. So the loss function, which is supposed to compare what I believe and what actually happened, gets affected for the next step, and it becomes kind of like a cascade, where does that kind of make sense? Is that making sense?
Yes.
So because like with grid world kind of stuff, every state is more or less separate. If I update this state, it doesn't affect what I believe about the next state, but with neural networks, it does. Then if you actually end up like, if you pull up one point and the next point is going to get pulled up, and then when you calculate loss, you're going to be comparing it against something that was affected by a previous one and becomes like this vicious cycle. And that's what they're trying to avoid. That explains the Q equals Q thing over there.
Okay, I'm sorry if I'm like the only one who's not still getting it, but so let's see. What? Yeah, I'm just trying to draw this, right? So let's say this is the network, right? Neural network. And then whatever. So, and let's say this is the RL. Let's say this one is Q-learning. RL agent, right?
What's the title of that first neural network? Is that the one that's converting state space?
That's what I'm trying to figure out. So let's say this is the camera. This is screen, right? Screen takes, and then from my understanding, like from your explanation, there is another network that actually part of the Q-learning, right? But how do you measure the policy?
So the neural network, it takes in the screen as input, and then what it outputs is action probabilities. Yeah, it doesn't predict the value of anything.
It outputs actions?
But
Yeah.
There's two in parallel. Where the and then there's actually two there.
Yeah, there's one.
Yeah, they're identical architecture and frequently identical weights as well, but not always.
If you look at the
They are both Q.
Yeah, that's the good, yes. Yes.
if you look at the algorithm, it's the one that's being updated all the time is being used to choose what action to take. And the one that's like the historical queue is used to calculate the Y.
Yeah.
The activation.
So what's the output of this network?
Action probabilities. One is just like it's just a copy. It's essentially like a cached version of this network at some state.
Okay, then I periodically kind of like
Update that.
Yeah. I don't think so. You have one that's like continuously updating.
I think
a certain amount of experience has to be accumulated. Yeah. And then you say, okay, copy the ways over to this one that is actually making the decision of what actually.
If I remember, there was an issue with like a positive feedback if they didn't have that mechanism.
Yes, so actually the action one does get, it's the reason to keep the old one is to make sure that you know what your loss is. That's the reason, because the loss can have a feedback loop where if you update the thing that you're comparing against, then you get what I'm saying.
There's something like
It's because the gist of Q-learning is to calculate a temporal difference. So you've got to have some kind of contrast.
Yes, exactly.
Then you update.
It's almost like, imagine if you're talking to somebody and they kept changing their beliefs about, like you're arguing with somebody and they kept changing beliefs every single sentence. You're like, I don't know where you stand anymore. And that's kind of what it's like. You can't calculate the difference if the person's constantly changing their beliefs.
But remember too, there's an issue with like if your predictor of what action to take gets better, then now your reward in the future also just got better, and it's like a positive feedback. So then if you just let your calculations stay at the old one, update your actions, and then update it every once in a while, you won't get caught in this trap, or it might just like dive straight on ahead on some action that produced a better probability of what action to take, which then also in turn increase your expected reward. It's a way to kind of slow that down. The paper does,
Okay.
I recommend watching that video like afterwards.
What video?
It's a Q that affects action. Q hat is just
Calculation.
And then later Q hat and Q merge, and then again Q continues Q and react about it. Q hat is just there.
Yes. What about the argument now? Like, I'm having an argument with someone, I'm trying to convince them of something I believe. I certainly have a world belief. I'm trying to correct that and say, oh, no, you believe what I'm saying because you don't know. If at every word I change my belief, I'm never going to convince you because I'm just chaotic. It's that nuts. Like, I can never learn. If I stick to the same belief for a while, people are going to agree, while at the same time generating a new neural network, which is kind of like a new belief that based on the arguments that you're accepting. And every now and then, through the course of the argument, I say, okay, you know what? This argument is working. Let's take this new kind of worldview and replace the one I'm using, and use that as my new argument strategy, while now again forming a new, as we discuss again, new network, kind of like reconciling the beliefs with this kind of like new worldview. So you're kind of always updating your worldview. And that's kind of what it is. So this string, which is leading to two neural networks, one of which will be current policy, which you're kind of continuously doing, and one of which will be your, I guess, the model you're creating to like update that policy, new one, which you're actually propagating backwards.
So this one is current belief, right?
Yeah.
Which dictates what?
Yeah.
Julian. Dictates what?
I think the actions you choose.
Yeah. Oh, you know, I figured out about that. It's dictating the rewards, right?
Yeah.
So, you know.
Okay, say it again. It dictates what? The rewards or actions?
I don't know. So I don't know where the actions come from. That's the thing I don't know.
It's the output. Yeah. So it calculates the expected reward that you're going to use in calculations.
Yeah.
I would just think to calculate the action. It doesn't when you just actions are analogous to the sentences. In the example. Otherwise, your agent, like, let's say your agent just starts from wild. You need to have a certain set of rules for the agent to follow. You need to have that constant. And only then can the agent actually move in the right way. And then as you learn that maybe is a better way to do it, and you merge the two things together, you get the best result.
Oh yeah, it is.
Yeah.
Which one?
Yeah.
Yes, it is. It's in your. It should be in your DLRL folder. You go to RL.
I think you basically saying something else. Everything else.
You see it? Okay, so let's maybe look at the video that.
Go with this.
Deep Q learning is an elegant algorithm that demonstrates how you can use neural networks to solve reinforcement learning problems. It has expanded the range of domains we can tackle, especially those with large and continuous state spaces. I'm sure you're eager to find out how it works. That's exactly what we're going to do in this lesson. We'll first take a look at how neural networks can be used to represent value functions. Next, we'll adapt the two main classes of model-free approaches, Monte Carlo and temporal difference learning, to work with this new representation. Remember that Q learning is a variant of TD learning, so this will prepare you to understand and implement the deep Q learning algorithm yourself. Finally, you'll learn how to harness the power of deep learning, including convolutional and recurrent neural nets, to teach computers tasks that seem almost impossible to learn from scratch, like playing video games.
No, it's Udacity. No, it's not. But we have.
So, how do neural networks fit into reinforcement learning? Well, remember how neural net.
What?
Udacity is free to audit, but you have to pay if you want to get the actual cert at the end.
All right.
Yeah, okay.
So, how do neural networks fit into reinforcement learning? Well, remember how neural networks are touted as universal function approximators? What if we use neural networks to represent our value functions? Would that work? Let's take a closer look. A state value function maps any state S to a real number, which indicates how valuable that state is according to the current policy pi. If we used a neural network to approximate this function, then the input would need to be fed in as a vector. Now, we already know how to do this using a feature transformation X. Okay, now the input can progress through the network, and if it is designed to output a single real number, that is our value, as estimated by the network. Great. This seems to fall in place with the general idea of approximating a value function with the weights of the neural network forming the parameter vector W. The question is, how do we learn these parameters? If we have a reference or target we're trying to reach, for example, v pi provided by some oracle, we can use the squared difference between the estimated and target value as our error or loss. Then we can backpropagate it through the network, adjusting weights to minimize loss. One popular method for adjusting weights is gradient descent, where we iteratively change weights a small step away from the direction of error. In order to apply gradient descent, we need to know the derivative of the value function represented by the network with respect to its weights. Now, this can become very complex, especially for networks with deep architectures. But we have pretty efficient algorithms implemented in libraries like TensorFlow, Theano, and MXNet to train neural nets for us. All we need is a way to figure out the loss, and that's where our knowledge of reinforcement learning comes in. At this point, let's also consider the action value function Q. The update rule looks very similar to what we had for the state value function V. But we have the same problem here. For most practical problems, there is no oracle to tell us what the correct value function v pi or q pi should be. We need to use a more realistic target, one that is based on our interactions with the environment. This is where reinforcement learning fundamentally differs from supervised learning. Next, we'll look at some strategies we can apply to find suitable targets to use in place of the true value functions in these equations.
So, do you follow? You understand what's happening?
Yeah.
Someone explain it to me in a simpler language.
For instance, I think
what
you're
if
saying is it's difficult to know what the value function at any given time is. Like you said, if it's sparse, you're not going to know immediately. So how do you resolve that sparsity problem?
Okay, but in this case, you take a state, you run it through your neural network, and the outcomes the value for that state, right?
How good do you think this?
Like imagine like in the Q learning paradigm, you have a table and a lookup table.
Yeah.
So that table is gone and it's being replaced by a new one. Yeah, because the table is too big.
Right.
It's too big that now you don't really have this precise state.
Yeah.
Then you have like continuous state that you can't really represent.
I see. So I see how you update weights. In this case, it's just a gradient descent, right? So I'm assuming in next step,
Only
will
after minimizing the loss. Yeah, only after minimizing the loss, because the neural network is what's going to, you're not using lookup. The neural network is the device that is used to determine the next state.
Well, not necessarily minimizing. You can do it online. One step at a time. You don't have to run all the way to.
Yeah, you don't have to run all the way through. That's correct. Yeah, but you need to minimize the loss in order to make, I guess, a more accurate prediction of the outcome. That's my understanding. Or the action that you're going to take.
Okay.
Our first strategy is to use Monte Carlo learning. Recall the incremental step that is used in classical Monte Carlo learning to update value functions. Here, GT is the return, that is the cumulative discounted reward received following time t. That's a suitable target to attain, isn't it? So let's take our neural network update rule and simply substitute the unknown true value function with this return. This gives us a concrete update rule for state value functions represented by neural nets or other function approximators. As you might have guessed, we can do the same for action value functions as well. Now that we have the main building block, the update rule, let's build a complete Monte Carlo algorithm around that. Let's focus on the control problem and adapt our classic Monte Carlo algorithm to work with a function approximator. It generally includes an evaluation step where we try to estimate the value of each state action pair under the current policy. We do this by interacting with the environment to generate an episode using the policy pi, and then for each time step t in the episode, we update the parameter vector W using the state action pair STAT and the return GT computed from the remainder of the episode. This is followed by an improvement step where we extract an epsilon greedy policy based on these Q values. At the beginning, we need to initialize our parameters W, let's say we do that randomly, and start with a policy pi defined in the same epsilon greedy manner. Then we can repeat these two steps over and over till the weights converge, resulting in the optimal value function and hence the corresponding policy. Note that this is the every visit version of Monte Carlo. For the first visit version, you only perform the weight update when you see the state action pair for the first time in an episode.
You have any questions?
Okay, I want to clarify, or I'm confused, like, is this filtering? This is not filtering.
No, this is Monte Carlo.
So this is not your filtering.
So Monte Carlo is when you go all the way, and then you try to calculate the.
After the episode finishes.
Yeah.
It's sample through the whole thing. And a lot of times even multiple episodes.
I see. So with my. Go ahead.
Defined by a fixed number of interactions.
Not necessarily. Okay, in the simple car poll example, the time balance the poll is when poll falls, episode ends. Okay. Essentially, you get over in a lot of cases. Or if it expires, it depends on when it runs.
The example that I learned with the Monte Carlo is when you drive, and let's say you and I reach your house in 10 minutes. You drive, you make sure, and blah, blah, blah. And then let's say you reach home like in 20 minutes. So 10 minutes, it's an error. And then you look back as like, I wish I turned this one. I wish I turned left. I wish I took highway. There was. So you make your adjustments looking back in your trip. So, but yeah, the episode has to finish before you can make any decisions.
Our second strategy will be to develop a temporal difference technique with function approximation. Compare the incremental update step between Monte Carlo learning, where we use the actual return obtained through the episode, with the temporal difference case, where we use an estimated return. This is called the TD target, and in the simplest case, TD0, we use the next reward plus the discounted value of the next state. In a similar manner as before, we can use this TD target in place of our unknown true value function. This gives us something concrete to work with, no more oracles or other imaginary creatures. Note that we had to adapt the value function to use our function approximator we had. This entire difference is called the TD error and denoted by delta t. We can extend the same idea to action value functions as well. All right, we're ready to build an algorithm around this update rule. We'll use a TD0 target and focus on the control problem again. As you may recall, this is essentially the SARSA algorithm. We begin by initializing our parameters W arbitrarily. Our policy pi is implicitly defined as an epsilon greedy choice over our approximate action value function Q hat. Then we start interacting with the environment. For each episode, we begin with some initial state S obtained from the environment. We continue interacting till we reach a terminal state. At each time step, we choose an action A to perform and observe the reward R and next state S prime. Now we choose another action A prime, this time from state S prime, according to our epsilon greedy policy pi. This gives us all we need for the SARSA update, S, A, R, S prime, A prime. We plug these into our gradient descent update rule and adjust our weights accordingly. Finally, we simply roll over S prime to be the new S, A prime to be the new A, and repeat. This formulation is useful for episodic tasks.
You were saying something?
S prime could be the new S.
So yeah, S is a state. So essentially, once you made all the calculations, because you're going back to S, you're updating like, okay, my new state, this is where I'm standing is my new S.
Right.
So essentially, you made a step. After you did all the calculation, you updated where you're standing now. That's your new S. W. Wait. Yeah.
So S prime is kind of like, it's just the same as ST plus 1. Right?
Yeah.
It's like the next state you get.
Oh,
and then the next time you do it, you're just like, this is my current state.
It's part of the iteration.
Yeah.
And the A's, why do you need to update A?
You have a loop, then you have that.
Well, the action you took is the next action.
Because you just need to remember what was your previous action.
Like, because you're gonna choose an action, and then now the action you just took is that one you chose.
You chose an action that you're going to be taking in the future in order to determine what the state, like the value of the present is the best to take in that state, right? So you're saying this is the state that what I'm going to choose, and that's the best. Well, you can't go back on your word when the next thing goes around and be like, decide not to do that. So you gotta stick with that.
It takes action A, but it doesn't take action A prime.
Exactly. Yeah, that's the next thing you're about to.
Okay.
Got it. Okay. Sian, you have a question? We can all answer.
I didn't keep going on this one. Like I covered like 10 questions.
Okay.
I have a
Any question?
yeah, I have a pretty good calculation here that I just posted.
Let's finish videos and then we'll go back.
Sure, yeah.
Where each episode is guaranteed to terminate. Can be adapted to continuing tasks by eliminating the distinct boundary between episodes and treating the sequence of interactions as one long, unending episode. SARSA is an on-policy algorithm. It means that we are updating the same policy that we are following to carry out actions. This usually works very well and converges pretty quickly because we are using the most updated policy to take each decision. But this also has some drawbacks, mainly that the policy being learned and the one being followed are intimately tied to each other. What if we want to follow one policy, say one that is more exploratory, while learning the more optimal policy? That's where we need off-policy algorithms.
Correlation is very high when you use this method.
What's the last thing that he said?
Okay, so the idea is
That's why we need off policy.
okay, so this is what I understood so far, right? If you do SARSA with one-step update, so essentially this is my state, I make one step, and based on this one step, I'm updating my policy. Then let's say at the very beginning, if you chose to go up in that grid world, right? And as you walk, this is the policy that you're updating. So as you update that policy, you're not really updating the policy that, what if at the very beginning, I took right and moved from the other side, right? Because that's the only policy you can see. As I'm making step, I'm updating this policy that I'm making right now. So that's why a one-step learning it's not as efficient. However, if you for every one step that you make, the policy that is being updated is influencing more decisions from the radius is greater. That's when you do a bit more of off policy because you have a bit more inside of the world as you update your stuff.
Okay, I seriously this on.
Can you go to the original paper? They actually talk about the algorithm, why it's model free and why it's off policy, and then it's useful to see.
This guy, eh? No.
No, that the human level control one.
This guy. Oh, wait a second. Fine. Oh, there you go.
So go down to where they explain the algorithm.
Which page?
Coming up, go up. Right there. Look over to the left. You look where it says, see training algorithm for DeepQ networks, that paragraph right above. So note that this algorithm is above that. This paragraph right here is key.
Oh, yeah.
Okay.
You learn about the GREE policy, but it follows a behavior distribution, not like following the policy. So it's off policy. Now, I don't know if any exploratory algorithm is automatically off policy because technically if you're going to take a random action, you're not necessarily following a policy. I'm not too sure about that.
You can have epsilon greedy, but still be on policy. Off policy, like, so you're following, you're learning by following some like different, like just super exploratory. It's not even epsilon greedy. It's just like, oh, we'll try step, see what happens.
Just like what it says in behavior distribution.
Yeah.
It's random, yeah.
Yeah.
So to answer what you're saying, it's also like, confirmation biases. is when you sort of like take a particular choice and you go, oh, I must have taken the right choice. And like you keep on constantly believing, instead of being like, maybe there were better choices out there. And so I think by not like not updating every single time, it's more scientific. You're just taking a broad spectrum of possible things and then making up your mind based on the data, instead of just sticking to one thing and being like, I must have been right because that's the decision I made, that kind of thing.
I mean,
That's, I'll give,
concretely, could you explain what broad spectrum is?
What is that?
broad
You
spectrum.
said broad spectrum, right? But how do you,
I think-
realize that broad spectrum?
Perhaps I can
But that would
explain.
just see more things.
Perhaps I can give you an analogy
It's-
to use it. So when you look at like so some people here are interested in behavioral finance. So in behavioral finance, confirmation bias is when you make a trade and all of a sudden it pays off, right? I just made some money. Yeah, it's looking good. I'm gonna do it again. Let's do it again. And an hour goes by and the trade's still going up, and all of a sudden it tanks. And why did I keep going?
Right.
When the average of the market continues to climb or decline. So by exploring a much bigger space or taking an average of something, then it's going to sort of neutralize your confirmation bias to continue making that trade on that one spot. So in this space, by exploring the state space, which is separate than each decision in that chain, and having that chain constantly back propagate and update the first decision, then you're separating the state space from the actual decisions that you're making. Okay? So in doing so, you're able to explore the state space, which is a much broader picture, and then using the exploration of the state space, you're getting a more holistic picture of whether the next decision is going to improve the net present value of the next state or not. It has to contribute back to the beginning where you want.
Okay, we're trying to figure out how to describe the epsilon gradient.
In the paper, if you look at the paper again, I'm gonna bring it up here.
The decisions are not determined by the policies learning. I think that's a one-liner. But not only, because he said it can still be on policy but exploratory. But
Okay, so like what is
Like the action doesn't change the rules that cover that.
That's right.
You making a step doesn't update the future or the neural network. What motivates you to take that step? The actions are determined by what motivates you to take that action. That's on. Okay.
that's on.
That's on.
Okay.
On policy is when every step that you take, you learn something new and then you update
Oh, I see.
what pushes you to do that next step.
Okay,
Yeah.
so you're continuously
Yeah.
updating.
all right, I get it. Yeah.
Yeah.
So that can lead you to go into a, like I can say, a suboptimal thing where you constantly,
Okay.
you're narrow-minded.
Yeah.
So you,
That's
you
right.
can
You get like
go
a
into
tunnel vision.
Exactly.
Yeah, like tunnel vision. Yeah, you don't see anything beyond the next state.
Okay. So the last sentence on that paragraph says in practice is done with the epsilon gradient thing, which means like, okay, I have a optimal policy based on what my experience so far, but every like maybe 1 out of 10 times I will do something like
Random action.
Yeah.
Okay,
But when you're not doing
then
random
that
actions,
is
it's
what-
policy.
and then update that.
By making it random, the statistical probability that you're exploring the entire space is greater than just being like, let's say, tunnel vision, going to the next one and I'm gonna back update.
So that's the exploration versus exploitation agenda.
Yes.
So like in the initial state, when you random initialize everything, you want your epsilon to be really large or really small. So you're always doing random things
Yeah.
and gathering experiences, right? And then once over the progression of your training, you start to formulate some sort of basis for your policy. And then you start decreasing the degree you choose random action.
Yeah.
Mhm.
But that is the exploration exploitation dilemma. I don't think this is what he covered here. So in the last sentence, when he was saying that SARSA, which is temporal one, essentially, let's say you make this decision, right? You go from this state to this state, right? That means you update the value of this state based on value on this state. So you're only updating this policy based on this information, right? So then you make, let's say here, and then you may update this state based on this state, right? So the
SARSA is always updated.
SARSA?
Yeah.
Yes.
Is it?
So this one is
Oh,
updating. Let me try to finish this thought, and then maybe I can address that. So you see, like as you go, you updating this policy, right? As you go. So from my understanding, what he meant is when you use one-step update, that's what you mean. Like you update one policy at a time. For example, this policy is being updated based on this policy that you follow. But the for example, the key learning is when you make this step, you update the radius of influence actually a bit greater. So the value of this state is being updated not only on this state but also on these two states.
Because of some random.
No, because of the way key learning like built
I
in
don't
general.
think the probability future rewards in the value state based on your current optimal or your current policy.
This is
I
sorry.
don't think that's how key learning works.
Okay.
From what I understand, so like I have my policy and I'm like, oh, this is what I think is the best thing to do.
Yeah.
Right. But the way that I get experience to learn from, I don't do what I think is best. It's not even epsilon greedy. Like I can have the epsilon greedy policy, but still on policy. Right. So key learning is off policy. So I'd be doing some other thing. I'd just it'd be like saying, oh, say let's for the sake of example, let me go to the right and then up, right?
Mhm.
That's not based on the policy that I'm actually going to use.
It's
Right?
random.
Yeah. It could be random or it could just be some other plan, right? It could be like saying, oh, let's try if we invest in Apple, let's see what happens, right? But that's not based on what I think is best. And then that information I get is used to update my actual policy, the stuff that I do think is best.
After a while.
Yeah.
Explore first and then explore.
But it's still not epsilon greedy. That's a different thing.
Right.
Yeah.
It's just
Completely
random.
Yeah.
Oh.
Completely random, or it could be deterministic, or it could be anything. It's just not necessarily what
It
you
just
think
says,
is
okay,
best.
let's try this thing out.
Yeah.
Let's collect experience for a while.
Yeah. And then you somehow use that to update your actual policy. And there's some
Okay.
like math going into
Okay,
that.
so that's the off policy.
Yeah.
Okay. So why is it not epsilon greedy?
So epsilon greedy is just like 1 in every 10 moves I do something new, right? But that's still not saying let's try something new, right? That's saying let's mostly do what I think is best and occasionally do something different. Off policy is like let's just try this completely new thing.
And randomize.
Yeah.
Greedy means just that. It's going to be greedy to have a particular outcome.
Yeah. Or it doesn't have to be random. It could just be like let's see what happens if I always go right. That's not random, but that's not my policy either.
Okay, I'm confused because EQN for each step it does say the probability of epsilon selected randomly.
So the part that makes it offline is as far as I know the experience replay part. So what I'm evaluating against is like what I did in the past. DQN kind of like complicates the whole key learning thing.
Okay.
But like key learning in its essence, you're using a different policy to learn from. I'm explaining it for you.
Let's watch.
Yeah.
But isn't Q learning? Isn't the idea of it is separate from the on policy.
Someone want to say something?
Q learning is off policy.
Yeah, but can't you have on? Because I think the basic Q learning model. Think about the avoiding the hole in lengths. Okay. That model essentially is just a Q lookup table that you're updating.
Okay.
But you can always follow the table, but then 10% of the time you do something random. That would be on policy, but it's Q learning.
Alok, you were saying something?
I think this one is not Q
I did want to just ask, who was it that was talking earlier? Sorry, I forgot your name. You were saying about the off policy part, because I was actually a bit unclear about that myself, because when I had been reading this paper, it seemed to me that the off policy had been the epsilon greedy part of it. But if it's not, I'm unclear.
From what I understand, I think I said Q learning is always off policy. I think I might be wrong about that.
It is correct. Yes, Q learning is off policy.
No, it can be on policy.
It says here, non-policy learning is a valuable policy to be carried out by the group. So by making it off policy, your performance of, like, say, gameplay, right? So if you've ever played like a first-person shooter game, you explore a state space. You know, you get this level, you go, okay, I better not go there. I better shoot here. It's no different than.
But you gotta distill it down to the bare bones. So learning. So let's explain them. There's a simple problem of trying to get across device. Or in the sheet of ice, there's a hole that you're gonna fall in and die. Similar to that robot one where you can fall in the fire or you get to the end. That is a Q table. You're following a policy based on epsilon percent of the time, you diverge, you do something random. So your behavior is dictated mostly by this table, by the policy itself. In case of this paper, they mention again in that same paragraph, or like right underneath it.
Yeah.
In practice, the behavior distribution is often selected by E epsilon greedy policy, follows the greedy policy with probability 1 minus epsilon, selects a random match for probability epsilon. That's like a traditional on policy. I think this one is off policy because its behavior is more being determined by what they go into in details, the experience replay, where it's not choosing something based on the current state, it's actually sampling memory. That's how it's learned. That's what makes
Oh, okay. I see. Thanks for the clarification.
I think experience replay is what makes
That's
this off policy, not epsilon.
It's not actually based on what it's seeing now. What it sees now, it just takes and stores in memory. Then, like it explains in the algorithm, you flip over a bit. But that's what makes us off policy, as far as I know.
Let's finish the video lectures real quick, and we'll try to.
Q-learning is an off-policy variant of TD learning. Let's see how we can.
I don't think that's correct.
Q-learning is off-policy variant of TD learning.
I don't see how like that original robot problem is off policy.
Let's see. Maybe it's a little bit. Listen.
Q-learning is an off-policy variant of TD learning.
Yes. I agree with that.
Yeah.
I don't think that's
I think key values are separate from Q learning.
That's right.
I think that's where the confusion comes in. So I can follow my Q table, and that would be on policy, right? But Q learning isn't just using a Q table thing. It's not.
All right, so let's keep going.
Yeah, just let them know that.
So Iagen GG. So it's me playing this thing now. How do I do this? Share my screen. All right. But I'm not enrolled in that program. How do I have access to that? Okay. Oh, he's back.
Oh, you're back.
Oh, never mind. Iagen's back.
He's back.
I'm off.
But can you guys actually see my screen though? Am I joined in the Hangout?
No, I think GM might have replaced.
No, I just joined this. But you're not in the Hangout anymore.
Yeah, so I need to go back so I can stream it.
Yeah.
GM has to hang out so he can.
Oh, no, he can just click on the link and join.
Yeah, I'm gonna click on this real quick.
What was that? The paper you guys are looking at? It's on Slack, right?
Yeah, everything is on Slack.
Okay.
Oh, this thing is still live, right? Okay. So,
Did you realize
my
something?
application.
What is it?
Can you?
Okay.
Can you?
I'll ask you later.
My speaker is on. Can you guys hear me?
Yeah, we can hear you.
All right, cool. Can we make it louder?
Action value function. But you could use like Sarsa.
Yeah, I was thinking my example is Q iteration.
Yeah.
But then their still novel idea was this idea of an experience gateway.
Yeah.
With function approximation.
I think it's good.
Just like Sarsa, we initialize parameters W arbitrarily and define an epsilon greedy policy pi based on the Q values. Over multiple episodes, we use this epsilon greedy policy to repeatedly take an action and observe the reward and next state. The main difference is in the update step. Instead of picking the next action from the same epsilon greedy policy, we choose an action greedily, which would maximize the expected value going forward. Note that we do not actually take this action. It is only used for performing the update. In fact, we don't even need to pick this action. We can simply use the max Q value for the next state. This is why Q learning is considered an off-policy method. We use one policy to take actions, the epsilon greedy policy pi, and yet another policy to perform value updates, a greedy policy. Although both of them are defined on the same underlying Q values, these two are indeed different policies. All right, this is what the Q learning algorithm looks like for episodic tasks. We can use the same algorithm for continuing tasks by treating the whole unending sequence as one long episode, or modify it slightly to remove the concept of episodes. Both forms are equivalent. In either case, we may need some additional criteria to figure out when we have fully learned the task or to detect if we are failing miserably. Let's take a moment to compare Sarsa and Q learning. Sarsa is an on-policy algorithm that follows the same policy that it is learning. In general, this is more suitable for online learning. At any point of time, you're using the most updated policy as per your interactions with the environment. However, it also means that if you use epsilon greedy action selection, which is necessary to encourage exploration, then this randomness also affects the Q values that are learned. On the other hand, Q learning is an off-policy method, meaning the policy it follows to choose actions is different from the policy it is learning. This can lead to bad online performance because there is a disconnect between the policy you're learning and the one you're following. But the good thing is that the epsilon greedy nature of action selection does not impact the Q values learned. Thus, the two approaches have their pros and cons, and which algorithm you choose will depend on the characteristics of the environment and your preferences regarding online performance versus more accurate learning. The biggest reason off-policy methods like Q learning have got so much attention is that they decouple the actions an agent takes in the environment from its learning process. That gives us the opportunity to build different variations of our learning algorithm. For instance, you can use a more exploratory policy while acting and yet learn the optimal value function. Yes, the online performance will be bad, but at some point we can stop exploring and follow the optimal policy for better results. In fact, the policy used to take actions need not be the agent's own. A human can demonstrate what actions to take, and the agent can learn from observing the effects of those actions. It also makes it easier to learn offline or in batches, since an update to the policy need not be performed at every step. This, as we will see, is critical for reliably training neural networks for reinforcement learning.
I can give you one example. One example comes to mind. is if you're creating a stock portfolio, you want to make sure that the portfolio goes by beta. In other words, its correlation or its lack thereof to the movement of the market. So if you have, say, 5 stocks in your portfolio and they have a beta of 1, they're going to be positively correlated to the movement of the market. The good thing about, say, Audi Starsa is because you want it online. As the trading day is going, it's going to be looking at the movement of the market and then looking at the correlation or lack thereof and make a decision or a prediction of, okay, where's the stock going to go next minute or the next point in that period. And then the third thing is that you can look at historical stock performance and train it to be even more accurate. Right? So that's one example that comes to mind. Sorry?
That'll be true.
What, using historical stock performance?
Can we, okay, before we go to the stock price, right? Based on this key learning, who got like intuitive understanding of it?
I'm still struggling with the on policy, but off policy is clear to me.
It's unclear?
Off policy is clear to me. On policy is really still like not clear.
Let's define ourselves like off policy and policy so we all know the same definition of it. So what is on policy?
Like my one liner would be the policy that you're learning is also determining your behavior.
That's correct.
Yeah.
I would agree.
We all agree with that.
Yeah.
Okay, what's off policy?
Policy that you're learning, like the behavior that you take is not coming from the policy you're learning, it's coming from something else.
Yeah, it's not directly tied to what you want.
Decoupled, like you
Yes,
mentioned.
yes, exactly. Decoupled. That's a more better word. If you want stuff high coupled, then Starsa, I would go with Starsa. Like for stock trading, right?
Like
You want
exactly.
you want highly
Stock
coupled.
market,
You
right?
want to look at the movement and then make a decision.
right away.
Highly
Because if you're
coupled.
taking a month's gap before you update what your decision's going to be, you
That's
can have
correct.
a stock at.
However, you could be off policy just like the way they did the Atari games, where they weren't learning from the current frame, they were learning from some sampled history.
Random samples, yes.
You think, okay, we're just gonna learn from some random history of the whatever stock you're trying.
Yeah.
I don't get in the example of stock. Nothing stock. If you are learning, training your network, you use your stocks algorithm. But while you are actually applying the algorithm, you just take out the epsilon part and you start using that right away. So in that sense, in terms of the final performance of behavior, they could both achieve the same thing. You can just take out the epsilon part out of the equation, and then your engine is online.
That's what he was mentioning too. It's like, imagine those Atari games again. If you're just constantly making choices based on some random distribution, not actually what's happening, your performance is going to be bad online.
That's correct.
But then as it gets tuned, you switch it over.
You need a greedy policy because every time you beat the game, you want to continue beating the game even more. And it's the same thing in picking a stock portfolio. You want to increase the gains you have to beat the market or to beat a portfolio or to beat a simple handful of stocks that you're trying to outperform. So you want to have a greedy policy. So, I won this time. I want more next time, and so on and so on.
So would that be, so let's say you are a MMA fighter. Let's say you're like a fighter or like a boxer in general, right? And let's say off policy would be watching other guys fighting and learning how to fight, right?
Yep.
Not learning how they fight, but learning like what makes a good fighter.
What makes
Okay,
you fight?
What makes
learning is, I think my understanding is you are based on my experience. I'm supposed to do this,
Yeah.
but I'm gonna try kicking.
What is that?
Once. That's
Okay.
off
Oh.
policy.
Off policy?
No,
Yeah, that's just for,
That's just exploration.
I would
that's
say
not off policy.
expert. You're trying anything.
Oh,
Yeah.
So off policy would be like, oh, I normally fight like Bruce Lee, but just this one time I'm gonna try. I don't know. another fight.
Fight
No,
like,
I think
Ip Man.
Yeah,
Ip
fight
Man.
like
I'll
Ip
try
Man.
fighting like Ip Man, and then use what I learned from fighting like Ip Man to update my Bruce Lee model.
that's right.
I think we're confusing the exploration and off policy.
Yeah.
Okay,
I'm confused. Okay, I'm confused.
I'm gonna go back again
No,
to
but what
the.
Austin said is correct, and it's the most simplest term that.
I'm gonna go back to the experience replay. So imagine you're boxing. Instead of actually realizing that he's throwing a right hook, you're actually seeing, okay, this is what happened when someone threw a left kick or a jab, and I'm gonna make this action. It's like you're not following your actual policy. It's just what's deciding what you're gonna do is just some other method, and like it's decoupled, so it can be anything. It can be experience replay, some other thing, blah blah. Okay, but on policy is like, okay, right hook is coming. I'm not gonna take a random choice. I'm gonna follow my policy, and right now my policy says that a right hook is coming. Best thing to do is duck or block or.
But
or
you're
parry.
saying that's exploration, so I tried about it.
Okay.
Let me try this.
Okay.
Like that example. Okay.
Yeah.
So your policy is your style of fighting, right? Let's say you fight like this. That's your policy.
Yeah.
Right? Arm policy is you will do the exploration of finding out new things, and then you'll learn like the movement style, but then you will not use that style. You will still fight like the Bruce Lee. Even though you've learned something new, you will still fight like. Even though you've explored, you will not choose a new. You will not deviate from your original action. You will still fight like Bruce Lee.
Yeah.
But the off policy is once you explored, then once you explored, wait, I think it's the opposite way.
Yeah, my understanding is
once
you get on the ring,
yeah,
and then you constantly keep changing
yeah,
your fighting style.
That's it.
You ones that you will change, and then the other ones you will not change. The opposite you will not change.
So
And
we're,
then the
we're
opposite
talking
is
about during training, right?
Yeah.
During training.
So like on policy Bruce Lee training would be like, I'm gonna fight like Bruce Lee and occasionally throw a kick, right? Or occasionally do a different move, because maybe something's gonna change, right?
But that occasional part is the epsilon BD.
Yeah.
That's just exploration.
So
That's not off policy.
That can still be on or off.
Yeah. So I'm still fighting like Bruce Lee. It's just once every 10 moves I get, right? Off policy would be like, okay, I normally fight like Bruce Lee, but I'm gonna try out Ip Man, right? And then maybe Ip Man worked, maybe Ip Man didn't, and then you have some way to like get your learnings from Ip Man and turn that into your Bruce Lee knowledge.
So essentially, you fight like a Bruce Lee, right? But then you watch, let's say, Ip Man fighting.
We watched the last part of that video.
Yeah.
Because there was a part that was really.
Okay. I'm getting it.
Cue demonstrate what actions to take, and the agent can learn from observe.
What?
Forward one when they were updating the learning.
Or they covered starts from at towards the
There was a formula. What more?
That's just some of the people before.
Here?
Yeah, let's sorry, yeah. Let's try that. Okay.
Okay, let me go a little bit further before they highlighted this guy.
The reward and next state. The main difference is in the update step. Instead of picking the next action from the same epsilon greedy policy, we choose an action greedily, which would maximize the expected value going forward. Note that we do not actually take this action. It is only used for performing the update. In fact, we don't even need to pick this action. We can simply use the max Q value for the next state.
Okay, it seems like it clicked with all of you. What happened?
Okay. So I think the yellow box would be like, I think Bruce Lee fighting style is the best, right? And Bruce Lee fighting style tells me I should have taken this action, right? And then our Q hat on the right, the minus Q hat thing, that's like what I'm actually trying out, right? I'm actually trying out Ip Man style, right? And then I see the difference. I see, oh, was trying out Ip Man a good thing?
Right, because of
Was
the
it not a
minus
good
sign.
thing?
It's a difference.
Yeah.
Okay, so this is what I'm doing.
That's what,
That's what I'm actually doing.
And
But the way I evaluate it is through Bruce Lee.
this is what I should have done right here.
That's what you. The S prime is always anticipated to be what's next. What you know. Yeah.
Like this is whatever you decide.
This is something S prime in theory is something you already observed. So take action and you get R and S prime.
That's right. R plus S prime.
But this is like whatever you say, like maybe you determine I'm always gonna act like Bruce Lee, right? So this is the reward I will get according to that fixed policy, and then you update it according to that. But the action that you actually take is something different.
It surprises me that it knows how to update the state based on this greedy action without following that through to conclusion. Is that following anything else too?
Say it again.
It's updating its policy, its reward state, its reward function, based on this maximal estimate of the reward of the next states. But it's not necessarily following that policy itself, so it's just assuming that it, but how does it know that it's still the reward?
Oh, so this is the discounted, what it's trying to do is follow the discounted reward for the best, like greedy approach. But it's not necessarily following a policy. So the one thing that's confusing me, it's not necessarily following a policy, it's just trying to learn from the best policy. How does it know? Is it because it's already seen the best ones so far? It's like remembering the last time it saw them?
It's like and it's important.
Okay, so it sounds like what it's doing is the difference is, it doesn't matter how it explores or whether it's exploring greedily or not. That's not on policy, off policy. What matters is how it updates its value estimation. So in the off policy case, it's following just, it could be following a random action, it could be following a greedy action, but it will only update its reward function based on what it thinks it's using its current model is the best reward. So it won't update randomly, it will only update based on what it thinks is the best. Doesn't matter what it does, it will do what it will update based on what it thinks is best. Versus on policy, it's updating based on what it actually does. So if it does a different thing, like a random thing, it's like it matters what the policy is. It's going to use that policy to update its reward function.
I know what you're saying, because what you're saying is like, I predict that if I take this action in this new state, there is a good action for me to take, but then when you actually get there, you don't actually take it. I think one of the reasons why it may not matter as much is because when you get to that next state, whether you take that action or not is not going to reciprocally affect what decision you made previously. Because this is updating, like this is saying currently, given my current state, how can I calculate what like the best action is given what I know about the future? Once I get into the future, I can't go back in the past and change my delta decision, because that's what I'm trying to do is determine like how to change my delta W, my weights. I'm going to update my weights, update my beliefs. Now I go to the next stage. Well, if it turns out I was wrong, I can't go back into the past and change my what I updated. So it doesn't really matter, right? Because you're going to be basing it on like it's like your current beliefs. It could be that you get the next stage and decide I'm going to try something else. I can't go in the past anyways. So, like that's what that's doing. It's updating your current beliefs based on what you think the future is going to be.
Yeah, it's forward looking, not looking at the past. It's forward looking.
Yeah. But when you get to the next step, well, if you were wrong, who cares? Because you can't go and update your beliefs in the past differently.
That's gotcha. Yeah. It's just using your past knowledge and saying, hey, if you can say anything better, just kind of iterate based on what we thought was best before. Yes. And if we see something better in the future, it'll update itself according to that.
To take a better action the next time.
Yeah.
Jian, you had some good insight.
Okay. I'm trying to wrap my head around. Okay, we're talking about like three steps here. S is
stage.
Okay, this is your starting point, and you have S and you choose an action, and resulting S and A here. And this is my current model. What I believe if I take it, I'm at stage S and take action A, what my future is going to be. What my value is going to be, like how much I'm going to get out of this. This is already done. And then it's essentially part difference between this part and this part. But this is the actual reward, what actually happened. Plus, there's a discount because I'm excluding the current step. I'm looking at the future step here. The next stage, like based on what already happened, and if I take action A and observe.
So what's confusing there is the lowercase a is actually a prime. It should have it's confusing.
Yeah, so there's a small cap A and then a big cap A.
This is about a lot of
S prime, A prime,
Those should be A prime.
So the small a is like your greedy policy.
That's right.
Oh, Xian, look.
And the big A is
I'm always confused.
currently falling.
So big A is whatever you pick from this policy. See, you have policy beforehand.
That's right.
You just follow this policy and you get this A. It's given by that policy. So yeah.
Yeah.
It's just given.
Action. The current action.
Yeah, imagine that you have some policy from somewhere. You already have it, right? So following this policy, following this policy, you choose action A from state S. You following that policy.
Which is the greedy.
Yeah. So this is the value for that Q that you get taking that action.
This is essentially I'm doing my best based on.
Like this is what happened. Like you
That's
can't go
what's gonna
back.
happen.
This is what happened.
Like this would be
This
like
is
I
what
don't have
happens.
and this is my assessment of the situation based on my current.
I'm pretty sure the thing on the right is the behavior distribution.
On the right.
The
This?
to the right of the yellow box. Yeah.
Yeah.
That.
Oh yeah.
That's your behavior thing, right?
Yeah. So this is like a real world. Like
Yeah.
what's happening? It's online, right?
Yeah.
But what about this part? What is this?
One is what you're going to do.
Okay, so the thing in the yellow box would be like, okay, so I do my Ip Man move, right? Maybe Ip Man like kicks for some reason, right? And then if I acted like Bruce Lee from then on, right? Then how good would that be?
Okay.
That's how
The
I'm
difference
understanding.
between the two.
Let's listen to this guy again on this yellow part.
Used for performing the update. Action from the same epsilon greedy policy, we choose an action greedily, which would maximize the expected value going forward. Note that we do not actually take this action. It is only used for performing the update. In fact, we don't even need to pick this action. We can simply use the max Q value for the next state. This is why Q learning is considered an off-policy method. We use one policy to take actions, the epsilon greedy policy pi, and yet another policy to perform value updates, the greedy policy. Although both of them are defined on the same underlying Q values, these two are indeed different policies.
Okay, so is it, am I right? Okay, so this comes after this, right? So we're talking about, this is kind of in the future, the next step. So it's a combination of what actually happened plus this part and the difference between this and this.
Yeah.
Essentially.
One thing I think I figured out that second time doing it, the thing on the right, the thing that was to the right of the yellow box, that doesn't even, it's not what we necessarily think is best, right? Yeah. And then, so then the max A, Q hat, whatever, then goes from like, okay, so after we do what we think is not best, like how would that work from there?
Wait, why is this not what based on our current this is what
That's, I don't think it is.
Well, why not?
Because that's our behavior distribution thing. It's just, it could be picking anything. Like I might know, or I might think that I know that Ip Man kick isn't best, right? But I'm just gonna do it anyways, right?
But
and then so what would the value of that be?
But this comes from the policy.
I had which is epsilon greedy. But epsilon greedy doesn't mean greedy.
Oh, okay.
Yeah. So the epsilon greedy policy could be initialized to Ip Man style.
Okay.
Right?
Or anything.
Yeah.
Oh, I see.
I had a bit of a light bulb there. So like essentially that function epsilon minus greedy, the Q hat.
Yeah.
That determines what action you're going to take.
Oh.
That is
Yes.
the action determining function.
Wait, can I say that?
It's policy.
That's what you're actually going to do.
This is what you
Now-
follow.
Yeah.
Yeah.
Now, as you see in the update, we aren't updating based on that action. We're updating based on the max of Q hat. It's a prediction given the next state. That's the two different models that we're using. Action comes purely from epsilon minus greedy Q hat given SAW. The action we're using in the updates is max of Q hat S prime AW.
So can I say that this happened in fact and this may be an imperfect action?
Oh yes.
And then this part essentially kind of evaluates how good this is, and then I'm gonna have
Right.
I can determine like if this is imperfect, I have a chance of evaluating whether it's suck or not.
That second part is given the action we're actually taking with capital A, and gamma max is like the greedy A, based on some prediction of the next state action and the
Yeah,
weight.
it's it represents epsilon minus the greedy.
Okay, so this actually is the what I think is optimal.
Yeah.
This is what I think future does.
That's correct.
Because this is like the weeks of the neural network.
Yeah, that first part is reality, which is like the real reward you get, plus a perfect version of what you would do next.
Yes, that's cool.
And then
Based on my current.
but what you actually did now as opposed to next may not be.
So then this has a chance of evaluating other actions.
Yes.
This is essentially that. Okay.
So the capital A is under the epsilon greedy scheme.
Yes.
Okay, so this is both the off policy and epsilon.
Off policy. Like if you replay the last 10 seconds, you kind of explain.
This is why Q learning is considered
More?
That's it.
an off policy method. We use one policy to take actions, the epsilon greedy policy phi, and yet another policy to perform value updates, a greedy policy. Although both of them are defined on this.
Yeah, so it's confusing to use the word greedy, but greedy just means perfect. Like the best option.
Yeah, the best, yeah.
But that's not the same as epsilon.
That's
Sorry
right.
about that.
It's just I always think action
No.
is the biggest.
Awesomest, yeah. If I do everything perfectly.
Okay, so
But it's based on S prime, and we're maximizing based on S prime. However, we're choosing based on S.
so we only have one Q learning, right? We only have one policy. This is the only Q that we updating and that we
Yes.
using, right?
That's what he mentions. Like if you keep playing it, he'll say we are using the same Q function.
Yeah.
Just let it play out.
So we are using the same Q function, but we take actions as epsilon greedy policy, but updating based on the
Yeah, it's the
classical
same
Q.
function, but the inputs of the function are different. That's what makes it two different like things you're using.
Same underlying Q values, these two are indeed different policies. All right. Value going forward. Instead of picking the next action from the same epsilon greedy policy, we choose an action greedy, which would maximize the expected value going forward. Note that we do not actually take this action. It is only used for performing the update. In fact, we don't even need to pick this action. We can simply use the max Q value for the next state. This is why Q learning is considered an off policy method. We use one policy to take actions, the epsilon greedy policy phi, and yet another policy to perform value updates, a greedy policy. Although both of them are defined on the same underlying Q values, these two are indeed different policies.
Yeah, essentially what I said wasn't necessarily correct. The inputs don't necessarily matter. It's just the fact that Q, S, some action W is a different function than maximize Q, S, A, W with respect to A.
So when do the Q values get updated?
But like you're also updating.
Which is W, right?
Right?
So then, but you.
Yeah.
W is the
Maybe
weight
this-
of
But then if that's happening every step, now that's similar to on policy. Right?
Because the way you're evaluating it is different. Like, so our epsilon greedy policy, the way I initialize it, I might know that that's suboptimal, right? But then the way I evaluate it, as far as I understand, is what I know to be optimal.
So it's either you take the next state or you take the state of which is more optimal in the space. It's either or, not both.
We have to based on
That's
Actually,
correct.
no, I guess the inputs do matter then, yeah, because it does, because you're updating based on this function, but it's like considering the future, and this is going to be.
Mhm. And if you're if you're discounting it back to the present, like for the action that you're going to take, and it doesn't significantly improve the max Q doesn't is better than what the action you're going to take, then you take the max Q.
Okay, let's try to watch the next
Sure.
video because I think that's where we go to deep part. If that wasn't deep enough.
In 2015, DeepMind made a breakthrough by designing an agent that learned to play video games better than humans. Yes, it's probably easy to write a program that plays Pong perfectly if you have access to the underlying game state, position of the ball, paddles, etc. But this agent was only given raw pixel data, what a human player would see on screen. And it learned to play a bunch of different Atari games, all from scratch. They call this agent a deep Q network. Let's take a close look at how it works. True to its name, at the heart of the agent is a deep neural network that acts as a function approximator. You pass in images from your favorite video game, one screen at a time, and it produces a vector of action values, with the max value indicating the action to take. As a reinforcement signal, it is fed back the change in game score at each time step. In the beginning, when the neural network is initialized with random values, the actions taken are all over the place. It's really bad, as you would expect. But over time, it begins to associate situations and sequences in the game with appropriate actions and learns to actually play the game well. Consider how complex the input space is. Atari games are displayed at a resolution of 210 by 160 pixels, with 128 possible colors for each pixel. This is still technically a discrete state space, but very large to process as is. To reduce this complexity, the DeepMind team decided to perform some minimal processing, convert the frames to grayscale, and scale them down to a square 84 by 84 pixel block. Square images allowed them to use more optimized neural network operations on GPUs. In order to give the agent access to a sequence of frames, they stacked 4 such frames together, resulting in a final state space size of 84 by 84 by 4. There might be other approaches to dealing with sequential data, but this was a simple approach that seemed to work pretty well. On the output side,
It's a sequence.
So it's like a different. Oh, I remember because you in some games like if you still frame, there's a ball there. You don't know its trajectory.
Okay, so
which one?
you get kind of like
So you get context by stacking four together.
Is
It
that
also slows down the robot, right?
It's not moving like insanely fast. Like
so? Those 4 frames at different times.
They're sequential.
They're sequential.
So you got
Otherwise, it could go up and
Yeah, like
realize no, I'm
velocity
supposed to go
and
down.
stuff.
because you want the S to capture the entire
Yeah.
thing, right?
It's basically gives you the
The
data.
4 essentially captures the entire space.
in order to give the agent access to a sequence of frames, they stacked 4 such frames together, resulting in a final state space size of 84 by 84 by 4. There might be other approaches to dealing with sequential data, but this was a simple approach that seemed to work pretty well. On the output side, unlike a traditional reinforcement learning setup, where only one Q value is produced at a time, the deep Q network is designed to produce a Q value for every possible action in a single forward pass. Without this, you would have to run the network individually for every action. Instead, you can now simply use this vector to take an action, either stochastically or by choosing the one with the maximum value. Neat, isn't it? These innovative input and output transformations support a powerful yet simple neural network architecture under the hood. The screen images are first processed by convolutional layers. This allows the system to exploit spatial relationships and consploit spatial space. Also, since 4 frames are stacked and provided as input, these convolutional layers also extract some temporal properties across those frames. The original DQN agent used 3 such convolutional layers with ReLU activation, regularized linear units. They were followed by 1 fully connected hidden layer with ReLU activation and 1 fully connected linear output layer that produced the vector of action values. This same architecture was used for all the Atari games they tested on, but each game was learned from scratch with a freshly initialized network. Training such a network requires a lot of data, but even then, it is not guaranteed to converge on the optimal value function. In fact, there are situations where the network weights can oscillate or diverge due to the high correlation between actions and states. This can result in a very unstable and ineffective policy. In order to overcome these challenges, the researchers came up with several techniques that slightly modified the base Q-learning algorithm. We'll take a look at 2 of these techniques that I feel are the most important contributions of their work: experience replay and fixed Q targets.
Did you guys
The
understand?
deep Q network is designed to
But isn't it just like it's almost like an image classification.
Exactly.
itself.
The deep learning part is
Like
Or-
this is exactly image classification.
Yeah, except the classification action.
Like you're just doing argmax out of all your possible classes, which
each individual one to display that.
All right, so our this network right there in the middle, this is our Q learning network,
Correct.
right? And the weights are the ones that we saw before being updated, right? Okay, so it's just like classification. At the end, it's just you classify actions.
If it's the queue, how come we didn't take action input as well?
Oh, one thing, the network, you know, the function approximation for Q learning,
Right.
there's a W. This is just a W.
Yeah.
Yeah.
Okay. But is there action in input? There should be action in input, right?
No.
It should be action
You
at
just
the
need the
same-
state. You don't need your previous action. You know, to
I
do
mean,
that.
it's like your action will propagate into what changed in the next state. So is it like manifested?
Yeah, it's like the state captures what your previous operator is.
Yeah, because you say, okay, go up, and then your screen changes.
Yeah. I don't need
And
to know
that's
that.
what-
But then, okay,
Right.
but then there's the part where you what evaluate in the future, the max of A, like the Q part, remember? R plus that, but that part you haven't recorded that.
Right.
But you have your previous state, right? So from my understanding, for every simulation that you have, for every action that you have, you run through this Q network.
Let's hear the experience replay.
Okay.
Okay, this is like a next lecture.
Yeah, just keep going. I think it's gonna explain our question.
Okay, sorry. Can you just show the next like real quick? No, the next slide.
Next slide, okay.
The idea of experience replay and its application to training neural networks for reinforcement learning isn't new. It was originally proposed to make more efficient use of observed experiences. Consider the basic online Q-learning algorithm where we interact with the environment, and at each time step, we obtain a state action reward next state tuple, learn from it, and then discard it, moving on to the next tuple in the following time step. This seems a little wasteful. We could possibly learn more from these experience tuples if we stored them somewhere. Moreover, some states are pretty rare to come by, and some actions can be pretty costly. So it would be nice to recall such experiences. That is exactly what a replay buffer allows us to do. We store each experience tuple in this buffer as we are interacting with the environment, and then sample a small batch of tuples from it in order to learn. As a result, we are able to learn from individual tuples multiple times, recall rare occurrences, and in general, make better use of our experience. But there is another critical problem that experience replay can help with, and this is what DQN takes advantage of. If you think about the experiences being obtained, you'll realize that every action AT affects the next state ST in some way, which means that a sequence of experience tuples can be highly correlated. A naive Q-learning approach that learns from each of these experiences in sequential order runs the risk of getting swayed by the effects of this correlation. With experience replay, we can sample from this buffer at random. It doesn't have to be in the same sequence as we stored the tuples. This helps break the correlation and ultimately prevents action values from oscillating or diverging catastrophically. Now, this might be a little hard to understand, so let's look at an example. I'm learning to play tennis, and I like to practice rallying against the wall. I'm more confident with my forehand shot than my backhand, and I can hit the ball fairly straight. So the ball keeps coming back around the same area to my right, and I keep hitting forehand shots. Now, if I were an online Q-learning agent, learning as I play, this is what I might pick up. When the ball comes to my right, I should hit with my forehand. Less certainly at first, but with increasing confidence as I repeatedly hit the ball. Great, I'm learning to play forehand pretty well, but I'm not exploring the rest of the state space. This could be addressed by using an epsilon greedy policy acting randomly with a small chance. So I try different combinations of states and actions, and sometimes I make mistakes, but I eventually figure out the best overall policy. Use a forehand shot when the ball comes to my right, and a backhand when it comes to my left. Perfect. This learning strategy seems to work well with a Q table,
where we have assumed this highly simplified state space with just two discrete states. But when we consider a continuous state space, things can fall apart. Let's see how. First, the ball can actually come anywhere between the extreme left and extreme right. If I tried to discretize this range into small buckets, I would have too many possibilities. What if I end up learning a policy with holes in it, states or situations that I may not have visited during practice? Instead, it makes more sense to use a function approximator, like a linear combination of RBF kernels or a Q network, that can generalize my learning across this space. Now, every time the ball comes to my right and I successfully hit a forehand shot, my value function changes slightly. It becomes more positive around the exact region where the ball came, but also raises the value for the forehand shot in general across the state space. The effect is less pronounced away from the exact spot, but over time it can add up. And that's exactly what happens when I try to learn while playing, processing each experience tuple in order. For instance, if my forehand shot is fairly straight, I likely get back the ball around the same spot. This produces a state very similar to the previous one, so I use my forehand again, and if it is successful, it reinforces my belief that forehand is a good choice. I can easily get trapped in this cycle. Ultimately, if I don't see too many examples of the ball coming to my left for a while, then the value of the forehand shot can become greater than backhand across the entire state space. My policy would then be to choose forehand regardless of where I see the ball coming. Disaster. Okay, how can we fix this? The first thing I should do is stop learning while practicing. This time is best spent in trying out different shots, playing a little randomly, and thus exploring the state space. It then becomes important to remember my interactions, what shots worked well in what situations, etc. When I take a break or when I'm back home and resting, that's a good time to recall these experiences and learn from them. The main advantage is that now I have a more comprehensive set of examples. Some where the ball came to my right, some where it came to my left, some forehand shots, some backhand. I can generalize patterns from across these examples, recalling them in whatever order I please. This helps me avoid being fixated on one region of the state space or reinforcing the same action over and over. After a round of learning, I can go back to playing with my updated value function. Again, collect a bunch of experiences and then learn from them in a batch. In this way, experience replay can help us learn a more robust policy, one that is not affected by the inherent correlation present in the sequence of observed experience tuples. If you think about it, this approach is basically building a database of samples and then learning a mapping from them. In that sense, experience replay helps us reduce the reinforcement learning problem, or at least the value learning portion of it, to a supervised learning scenario. That's clever. We can then apply other models, learning techniques, and best practices developed in the supervised learning literature to reinforcement learning. We can even improve upon this idea, for example, by prioritizing experience tuples that are rare or more important.
Can I give you an example, a really great example of this? Experience trumps everything when it comes to human cognitive function, right? So when you see guys like Mark Zuckerberg or Bill Gates, what the difference between them and everybody else is that they have tens of thousands of more failures than the average person does. Because failing from experience is the best way of reinforcing the outcome that you want. In the conventional method that everybody learns, you go to school, you climb a ladder, you do things sequentially, and failure is not rewarded, right? You fail a course, you fail a course. However, entrepreneurship, you hear the word of fail big, fail fast, fail often, and that's because it works. So massive disruption or reinforcement is done through a lot of failure in a very short period of time, if at all possible. And this is what makes people like that so effective at solving problems. And it's the same thing with AI. When you have a lot of reinforcement through failure, it learns fast and it becomes very, very effective. The deeper the neural network and the more failures you expose, theoretically, it should get better, really, really better, and it should supersede us eventually. Right? Make sense?
Yeah. So for the experience replay, the analogy that I can think of is like a dream, right? That's what they had. And I guess the point why this one is so valuable is if there's some cases that you see rare in real life, in your dreams you can actually practice them more often. Is that?
Yeah, like, okay, so I studied Kung Fu 13 years. So there is really little difference between me closing my eyes and practicing a move and me physically doing it.
Okay.
And like when you think back to the conversation you had, you asked about your sense of familiarity.
Yeah, like yeah, exactly. Like in Chinese, I'd make mistakes all the time, right? And I'd walk away and go, oh, I should have said this. Oh, I should have said that. You replay these conversations. I'll go home and I'll retranslate. Okay, that's the way I should have said.
Yeah. It's one of my philosophies here. I try to explain things a lot and try to give answers, end up being wrong.
Well, so
it's sort of choosing an action. You can't rewind and see what other outcomes there were.
But the next
you
time,
just see how bad the action you
that you chose. Exactly. Yeah. So it's not
I would argue a little bit
right
though.
or wrong, it's about effectiveness. That's
Brian,
really
go
what
ahead.
it is. Sorry. It's not about being right or wrong. It's about effectiveness
Right.
or ineffectiveness. That's the goal.
Okay. Brian, you were saying something?
Yeah, I was just gonna say I like the analogy, but I guess the truth is, like, from my understanding and everything I've learned in biology and in human cognition, excess failure, especially actually in a short window of time, sometimes leads to actually badly learned behaviors and things like probably bad addictions and stuff like that, or even avoidance type stuff, which I guess is just part of the human sentiency and something that we're not really talking about here, though.
Yeah.
Okay. Good points. Like if you
I
fail,
agree.
it's like, oh fuck, I'm just not gonna bother anymore.
But remember, these those type of failures is always kept in the premise of some kind of reward, and that reward is success, whether it's monetary success or something. That is typically the reward is positive. Now there are a lot of negative incentives for, like, say, I need my next fix of drugs or something, right? Then you're going to do negative behaviors. Each one of them cognitively have the same outcome, the reward.
Well, there's a lot of research now going into like social defeat syndrome and social defeat stress and even the neurobiology around it. I guess I would argue what makes Bill Gates and those people so special and successful is their resiliency and the fact they have some intelligence and wiring, or somehow even adapted and through epigenetics or whatever it was, changed through their experience to the point that they were able to grow from adversity and always use that in a positive way. Whereas some people emotionally can't do that as well. And there's also that whole aspect of when you think of the corporate ladder and all that stuff, they get into stuff like the discussion of psychopathy and how by doing things maybe cruel, but not excessively cruel for your level of comfort, you can slowly desensitize to the point that you don't feel bad laying off maybe 20,000 employees, even a few hundred guys that you know have important. So all those little like specifics that I would say, I like your analogy, but I think to generalize is a little strong there.
Okay. So I just want to bring it from like philosophical back to practical.
Okay.
Looking at number 12 is TensorFlow implementation.
Yeah, so
we have 13
let's
minutes. I don't know if we can.
let's try to just watch.
Sure.
Let's try to watch as much as we can, and then we'll.
Experience replay helps us address one type of correlation, that is between consecutive experience tuples. There is another kind of correlation that Q-learning is susceptible to. Q-learning is a form of temporal difference, or TD learning, right? Here, R plus gamma times the maximum possible value from the next state is called the TD target. And our goal is to reduce the difference between this target and the currently predicted Q value. This difference is the TD error. Now, the TD target here is supposed to be a replacement for the true value function Q pi SA, which is unknown to us. We originally used Q pi to define a squared error loss and differentiated that with respect to W to get our gradient descent update rule. Now, Q pi is not dependent on our function approximation or its parameters, thus resulting in a simple derivative and update rule. But our TD target is dependent on these parameters, which means simply replacing the true value function Q pi with a target like this is mathematically incorrect. We can get away with it in practice because every update results in a small change to the parameters, which is generally in the right direction. If we set alpha equals 1 and leap towards the target, then we'd likely overshoot and land in the wrong place. Also, this is less of a concern when we use a lookup table or dictionary, since Q values are stored separately for each state action pair. But it can affect learning significantly when we use function approximation, where all the Q values are intrinsically tied together through the function parameters. You may be thinking, doesn't experience replay take care of this problem? Well, it addresses a similar but slightly different issue. There we broke the correlation effects between consecutive experience tuples by sampling them randomly out of order. Here the correlation is between the target and the parameters we are changing. This is like chasing a moving target, literally. In fact, it's worse. It's like trying to train a donkey to walk straight by sitting on it and dangling a carrot in front. Yes, the donkey might step forward and the carrot usually gets further away, always staying a little out of reach. But contrary to popular belief, this doesn't quite work as you would expect. The carrot is much more likely to bounce around randomly, throwing the donkey off with every jerky step. Each action affects the next position of the target in a very complicated and unpredictable manner. You shouldn't be surprised if the donkey gets frustrated jumping around the spot and gives up. Instead, you should get off the donkey, stand in one place and dangle the carrot from there. Once the donkey reaches that spot, move a few steps ahead, dangle another carrot, and repeat. What you're essentially doing is decoupling the target's position from the donkey's actions, giving it a more stable learning environment. We can do pretty much the same thing in Q-learning by fixing the function parameters used to generate our target. The fixed parameters, indicated by a W minus, are basically a copy of W that we don't change during the learning step. In practice, we copy W into W minus, use it to generate targets while changing W for a certain number of learning steps. Then we update W minus with the latest W, again learn for a number of steps, and so on. This decouples the target from the parameters, makes the learning algorithm much more stable and less likely to diverge or fall into oscillations.
That's a very important.
That's a question. Okay.
That's a very important concept to understand.
We're now ready to take a look at the deep Q-learning algorithm and implement it on our own. There are two main processes that are interleaved in this algorithm. One is where we sample the environment by performing actions and store away the observed experience tuples in a replay memory. The other is where we select a small batch of tuples from this memory randomly and learn from that batch using a gradient descent update step. These two processes are not directly dependent on each other, so you could perform multiple sampling steps, then one learning step, or even multiple learning steps with different random batches. The rest of the algorithm is designed to support these steps. In the beginning, you need to initialize an empty replay memory D. Note that memory is finite, so you may want to use something like a circular queue that retains the n most recent experience tuples. Then, you also need to initialize the parameters or weights of your neural network. There are certain best practices that you can use. For instance, sample the weights randomly from a normal distribution with variance equal to 2 by the number of inputs to each neuron. These initialization methods are typically available in modern deep learning libraries like Keras and TensorFlow, so you won't need to implement them yourself. To use the fixed Q targets technique, you need a second set of parameters W minus, which you can initialize to W. Now, remember that the specific algorithm was designed to work with video games. So for each episode and each time step t within that episode, you observe a raw screen image or input frame xt, which you need to convert to grayscale, crop to a square size, etc. Also, in order to capture temporal relationships, you can stack a few input frames to build each state vector. Let's denote this pre-processing and stacking operation by the function phi, which takes a sequence of frames and produces some combined representation. Note that if we want to stack, say, 4 frames, we'll have to do something special for the first 3 time steps. For instance, we can treat those missing frames as blank or just use copies of the first frame. Or we can just skip storing the experience tuples till we get a complete sequence. In practice, you won't be able to run the learning step immediately. You'll need to wait till you have sufficient number of tuples in memory. Note that we do not clear out the memory after each episode. This enables us to recall and build batches of experiences from across episodes. There are many other techniques and optimizations that are used in the DQN paper, such as reward clipping, error clipping, storing past actions as part of the state vector, dealing with terminal states, decaying epsilon over time, etc. I encourage you to read the paper, especially the methods section, before trying to implement the algorithm yourself. Note that you may need to choose which techniques you apply and adapt them for different types of environments.
So what we're trying to do now is to watch as many as we can by the time it's 6, maybe in like 5 minutes.
Yeah.
Several.
That's one. Yeah, we're not gonna get through this.
Yeah, we're not gonna get through this. So
This is a really.
Well, I think discussing is also the important part too.
let's just talk about it,
It's a
right?
great start. Yeah.
Yeah, I got a quick question though. Do you have a link to these? Because when I tried just going to Udacity, there was all this login stuff and things like that.
This course is not free and you have to. It's on YouTube. I tried looking for.
No, these are definitely private.
Yeah.
Can you?
Several improvements to the original
You can only get one at a time.
It might be because you have the link. It's unlisted. Yeah, you need the link.
Okay, so this is somebody's their own account with Udacity.
So, and it's like talking on it.
Okay, never mind then.
Good, thank you.
You pay for it? Yeah.
That'd be great.
This is a deep learning foundation.
Deep learning foundations?
Yeah.
Interesting. Okay, so just in 4 minutes, right? I think we are still trying to get some intuition. It's a bit more clear. It's a bit more complex than we anticipated, at least for me. Yeah, but I think what we can do is there are these videos. We can go over the videos that Jake will post. Then we can go over the paper that was shared from the Stanford with the Q-learning. Let's just go over them over the next week. Make sure we understand all the concepts, methods, and polish it. So next time we meet, we already have a good understanding of what's happening and maybe just troubleshoot. Like if you're still like floating somewhere, we can explain to each other what's happening and start coding. Like next week is going to be mainly learning that tool at the MIT deep traffic code, and maybe even look at how to implement in TensorFlow as well, if we can get this.
One thing about that deep traffic paper, though, isn't the paper the point of crowdsourced hyperparameter tuning? Like it doesn't actually explain what algorithm won based on. It's like a
practical merit is where the aspect is looking at it. I mean,
So I thought basically we have to come up with our own type of model to compete.
No. That was my example when I looked at it. There's examples online. You get to learn the fact network size, temporal dynamics, discounting of rewards, and impact of green. So those are important things you do learn.
Yeah.
There's some practical aspect. I think I seriously I feel it deviates a little bit from.
That's what I was thinking. Maybe we apply the world model to that game. It's like a way to try to do two things.
Does the world model you
You can even look at past examples of because this is the second year, right? You can look at what happened in the first year. So now we put a code and what motivates me to what they did.
Or yeah, we re-implement some guy's code that fucking like did amazing on it. Like,
yeah, we can like use it as a starting point. That'll be very good to get our own.
Or start simple, like if we just like try applying like straight up learning and then like kind of the algorithm as a deep component, try mini batch, we can see I guess the improvement.
part I don't like is like we got to do this in JavaScript.
Yeah. Does anyone else have experience in JavaScript?
I don't know much JavaScript.
I'm fully
Yeah, right. Fluent?
Yeah, I was well.
Oh, nice.
I hear it.
Oh, nice. Okay. Then.
I know all these things.
Coding JavaScript long time.
I'm not even really interested in learning JavaScript.
Well,
eventually we will.
Yeah,
JavaScript. I'm avoiding anything client.
No, actually, JavaScript it's also the backend.
Node.js, but that's not like.
Oh,
Are we talking about the language, right?
TensorFlow has TensorFlow.js.
I know,
also on our browser, and we wrote we're
JavaScript
looking at
is too janky of a language.
Ah, that's crazy, man. That's crazy.
For yeah, the memory limit for browser is 40. Oh, let's just imagine and it's a lot slower. It's WebGL, so
Told the guys online. Do you guys have any questions? Alok, Emmy, Bilal, Brian, Shops, Willie.
I don't have any questions per se, although I do want to point out that well, you close the video now. Next time. There's the fixed Q targets part is I think the important part to look at there.
Fixed Q target?
The fixed Q targets. So I think that's really the question we have about the offline and offline part.
Oh, I see. Okay.
And I, just to motivate people, can I propose that next time at the beginning we randomly pick a person and ask him to write down the entire algorithm?
Or off.
Well, I'm up for that.
Anybody up for that challenge?
Yeah, I'm down.
Also, I'm glad that this used that original paper because now we have like 2 layers of compression. You can read the original paper, then try to watch the TDLS summary of the paper, which is like an hour long, and then you can even go back to this. It's like there's layers of how nitty gritty you want to get into the details and other explanations. The TDLS video also has different ways, different analogies, more discussion. It's nice.
Great.
I also posted 2 papers for financial reinforcement learning.
Uh-huh.
I did mention on TDLS that I want to tackle reinforcement learning right up to the code and present it. I can explain relating to stock trading. I think it'll be very valuable.
Willie, Brian, do you guys have any questions or comments?
It's in the general though.
Yeah, not so much any specific question. I just know that you need to clarify. So I'm going to go through the material through the week like we're talking about and make sure it's fully understood.
All right.
Yeah.
Brian?
I have a question. Oh, sorry.
Yeah, I don't really have any questions. I'm like just reading about the Bellman equation and where it's derived from, but I don't think we should get into that now.
Oh, look, you're saying something.
Sorry for interrupting. I had one question. So you said the TDLS video, that's not the same as the MIT video that we were talking about, right?
No, TDLS did a paper, like did a presentation on the DQN paper.
On that paper, yeah.
Okay.
So
That's in the other Slack.
There's a 1 hour recording. I don't think it's on Slack. In fact, I'm posting.
I posted a link on DLRL in general, but if you search in the TDLS channel, like Reddit,
yeah, just do
Reddit TDLS human level control, you'll find it.
Okay, got it. Yeah.
I have a question then for that. Is there something, are you guys recommending that video? There's something more to it?
If you value the TDLS presentations and you missed that presentation, then I'd recommend watching.
Yeah, that's one to watch.
Yeah.
I was
Okay.
live. Like I didn't actually watch, but yeah.
Okay, Bilal, do you have any comments, questions? Yeah, we cannot hear you. All right, we'll do that, yeah. Amy, Shabs, do you have any comments, questions?
No, not at this time, thanks.
Okay, great. Thank you. Shabs?
Yeah, I'm good. Just in terms of sharing that Udacity module, because that's a private login, is that something we could probably purchase like separately and just share with the team?
Sure, you can.
He's gonna share the YouTube link for it. Yeah, I'll get the YouTube link. But if you're interested in purchasing a course, you can just sign up.
Yeah.
Isn't it stopping like the entire group purchasing a course and then we all have access to it as a group?
It's around 1700.
But then across all of us, it's like nothing, right? And then we all have the same login, but anything that would stop.
But I mean, like,
If you want a video, they're all published on YouTube.
It's unlisted though.
Unlisted, yeah.
Technically, it is public because it's on YouTube.
Yeah.
Someone can delete.
Someone just need to go through the trouble.
And the paper for this,
You
the
can
paper.
still find it. The Udacity has a massive playlist, like hundreds of videos.
Yeah.
So you can just have to.
On this, you'll never find it searching YouTube. Though. Like you need the link.
Yeah.
All right, guys, we are wrapping up. I'm gonna screen sharing. I'm gonna go offline.